All right, welcome to Mission Control, everyone. I'm your flight director, and today we are going to be treating your Cambridge 9618 computer science exam exactly like a critical flight system. You see, in this environment, every single input matters, every calculation uses up precious fuel, and honestly, just a single structural error can send you entirely off course. You are our pilots in this explainer simulation, and our absolute primary objective today is mastering character data representation. Specifically, we're zoning in on the ASCII character set. We're going to lock in on the exact telemetry you need to clear orbit and secure those maximum marks. So strap in.
Okay, let's dive straight into this. We recently intercepted a transmission directly from Cambridge Command, and the senior examiner stated something you absolutely need to hear. They said that this topic appears in every examination series. Think about that for a second. You literally cannot avoid it. It's completely foundational. Honestly, it's like the atmospheric pressure of the entire exam. If you don't understand how character data fundamentally operates at a binary level, like how the uppercase letter A maps exactly to the decimal value 65, you're basically flying blind. We need to ensure that your navigation systems are perfectly calibrated for this completely unavoidable encounter.
So here is your mission flight plan for today. We'll start with Phase 1, pre-launch telemetry and theory. Then move to Phase 2, approach trajectory and methodology. Phase 3 is our Peel Radar Challenge. Phase 4 covers debris detection and common pitfalls. And finally, Phase 5, the touchdown checklist. Let's prep for launch.
Initiating Phase 1, pre-launch telemetry and core principles. It's time to lock down the theoretical architecture of character data.
Now, to guide us through this theoretical foundation, I really want to introduce our two test pilots for today, Pilot Alex and Pilot Sam. Both are highly capable students, but their flight telemetry shows some very distinct vulnerabilities that you might actually recognize in yourself. Pilot Sam, in particular, has a habit of just memorizing what ASCII stands for and calling it a day. But here's the thing. Examiners, who are essentially our flight evaluators, target three specific cognitive domains: knowledge, application, and analysis. If you ignore these specific parameters and fail to actually apply or analyze the binary conversions within a given real-world scenario, you're going to experience a massive systemic breakdown in your scoring. You absolutely have to satisfy all three of those telemetry sensors to pass the checkpoint. Just knowing the definition simply isn't enough anymore.
And looking at the principal examiner reports, they make it crystal clear that top-performing students, our elite commanders, exhibit a highly connected conceptual understanding. They are achieving significantly higher marks by connecting ASCII concepts to other, sometimes totally unfamiliar syllabus areas. Character representation doesn't just float around in a vacuum, right? It connects deeply to algorithmic efficiency, it connects to data structures, and it directly impacts system hardware. If you really want those maximum marks, you absolutely must establish these cross-topic communication links during your flight. You have to see the bigger picture.
All right, transitioning right into Phase 2, monitoring the approach trajectory. We've got our theoretical foundation built. Now we desperately need some tactical methodology.
Okay, we are observing your trajectory right now, Pilot Alex, and we need you to stop burning fuel on overcomplicated, messy calculations. What you need to do is adopt this precise 5-step procedural framework. Step 1, identify the key elements given to you in the exam prompt. Step 2, apply the relevant ASCII and data representation principles to those elements. Step 3, execute your analysis with completely clear step-by-step working out. Step 4, verify your results. Ask yourself, is this reasonable? And Step 5, present it in the exact precise format the examiner requested. If you follow this standardized sequence every single time, you process the problem systematically, and it brilliantly illustrates how to completely eliminate that panic-induced time burn we all hate.
Now, during this approach trajectory, I cannot stress enough that your data interpretation skills are absolutely critical. You've got to be able to smoothly extract data from binary representations and convert them flawlessly to ASCII values, and vice versa. But look, just extracting the data isn't enough on its own. You have to perform precise calculations and then, and honestly, this is the really crucial part, draw evidence-based conclusions from them. You aren't just acting as a human calculator here. You are a systems analyst. You're interpreting what that specific 7-bit string actually means for the overall system's performance.
I really need all pilots to pay very close attention to this next directive: engage the method mark strategy. Guys, this is your ultimate safety net. Cambridge examiners actually award marks for the process, not just your final mathematical answer. If you show clear working and a systematic analysis, you are actively securing partial marks even if a minor calculation error happens during a bit of exam turbulence. Never ever just write down a final binary or decimal number on its own. Show your flight path, document your trajectory, earn every single one of those method marks.
All right, we're going to pause the simulation just momentarily here. Before we fire the secondary boosters to push through the absolute hardest phase of this exam trajectory, you need to make sure you're optimizing your own flight path. Subscribe to Ace the Exams at the handle @AceTheExams right now and turn on all those notifications. Consider it your permanent, direct link to mission control. We are here to provide the exact coordinates you need for top grades, so lock that in and let's resume the simulation.
Resuming flight. We are now entering Phase 3, the Peel Radar Challenge. And heads up, we require an immediate structural override to save this trajectory.
Our telemetry is indicating a major roadblock right now. Our crew's comparative analysis is failing mid-flight. They are just listing generic facts instead of actually evaluating them against the specific problem context. So we are injecting the Peel structural template directly into your answer framework to fix this right now. Let's break it down. P is for point. You absolutely must identify similarities and differences when comparing data representation methods. Don't just do one or the other. E is for evidence. You have to pull specifics directly from the exam scenario they gave you. E is for explanation. Use comparative connectives. I'm talking about words like whereas, conversely, or however. And finally, L is for link. Draw a solid conclusion about their relative importance. Doing this deconstructs those incredibly complex comparisons and forces you to actually justify your decisions with evidence, which is exactly what top-scoring candidates do to pull ahead.
Moving right along into Phase 4, debris detection and examiner warnings. Keep your shields up, everyone. We are officially entering the historical crash sites of previous candidates.
Scanning the debris field right now, and we have identified the top 3 traps that routinely take candidates out. Trap 1. It's the classic mistake of using the wrong formula or algorithm for the wrong context. Look, just because you memorized a conversion method doesn't mean it magically applies to this specific piece of hardware described in your prompt. Trap 2. Forgetting boundary conditions. Pilot Sam, this is completely your sector. You have got to check the structural limits of the data types you're working with. And Trap 3. Missing the edge cases entirely. These 3 errors right here, they routinely crash candidate scores, so we have to navigate around them.
Let's initiate a live radar challenge to really see this in action. Imagine a generic answer states, ASCII uses 7 bits to represent 128 characters. Well, that right there is a system failure. Yes, it's technically true. Those 7 bits do give us 2 to the power of 7 unique permutations, which means exactly 128 distinct alphanumeric characters and control codes. But guess what? It earns 0 marks if the question is actually about a specific embedded device's memory constraints. Now look at the context-specific answer. It says, because the embedded sensor only has X bytes of memory, the 7-bit ASCII representation allows all 128 necessary alphanumeric inputs to be stored without exceeding the hardware limit. Do you see the difference? It links every single technical point directly to the scenario. That is how you get maximum marks. So the crucial point is this memory hack to help you bypass those examiner traps forever. I want you to remember the acronym CEB. C means context-specific answers always. Never ever just write a generic textbook definition. E means edge cases must be checked. You've got to test the absolute extremes of the algorithm. And B means boundary conditions verified. Always ensure the data actually fits within the allocated memory or structure. If you lock CEB into your navigation computer today, you will fly right past those common hazards without a scratch.
All right, we are officially clearing the debris field. The approach vector looks absolutely perfect. We're entering Phase 5, mission accomplished, and touchdown. It is time for your final pre-flight scan.
Pilots Alex and Sam have successfully touched down. They utilized the 5-step procedural framework, they applied the Peel structure perfectly, and they deployed the CEB hack. Now, before you open your actual exam paper, I want you to run this algorithmic thinking pre-flight checklist in your head. First, step-by-step decomposition. You need to break the ASCII problem down into logical, manageable parts. Second, appropriate data structure selection. Decide exactly how this character data is best stored. Third, efficient code implementation. Make sure you write clear logical pseudocode or step-by-step working. And finally, rigorous testing protocols. Mentally run some dummy data through your solution to check for reasonableness and any potential trade-offs.
The simulation is complete, but honestly, your real mission is just beginning. I want to leave you with this absolutely critical question on your console. Have you rigorously tested your own algorithmic thinking against a past paper today? Just watching this telemetry is not enough. You've got to get into the simulator yourself.
I challenge you to deconstruct a past paper question right now using the exact procedural frameworks we just established. Test your limits today before exam day tests them for you.
Well, this is Mission Control officially signing off. To ensure you receive all future telemetry and tactical masterclasses, make sure you subscribe to @ACE the Exams and enable that notification bell. I want all of our focused learners to report to the debriefing room right now. Drop a comment below sharing your specific subject and tier so we can calibrate our very next flight simulation exactly for your needs. Keep your flight paths optimized, and I will see you in the next explainer.